Hello and thank you for watching my video. Today we will be covering Chapter 8, IP addressing. This is part of CCNA Semester 1, Introduction to Networks. This chapter will be covering, is divided on 3 sections. We have section 8.1, IPv4 network addresses. In this section we describe the structure of an IPv4 address, describe the purpose of the subnet mask, compare the characteristics and uses of the Unicast, broadcast, and multicast IPv4 addresses, compare the use of public address space and private address space. Then we'll move on to section 8.2, which is IPv6 network addresses. In here we explain the need for IPv6 addressing, describe the representation of an IPv6 address, describe the type of IPv6 network addresses, and then we'll move on to section 8.3, connectivity verification, configure global unicast addresses, describe multicast addresses, describe the role of ICMP in the IP network, including IPv4 and IPv6, use ping and traceroute utilities to test the network connectivity. Okay, we start with section 8.1, IPv4 network addresses. Binary notation. Binary notation is a representation of information using only ones and zeros. So in the computer language, uses binaries, only ones and zeros to represent pretty much anything, any different type of forms of data. Any pictures you see on the screen, any documents you're reading on the screen, websites, emails, everything is represented with zeros and ones. Positional notation means that a digit represents different values depending on the position the digit occupies. So if you look at, we see the positional notation for decimal numbers. We know, for example, 192. How do we know that it's 192? Because the positional where the numbers are located. For example, we don't have anything under the 1000s, but we have 1 under 100s. So, and then we have 9 under tens and 2 on units. So when you think, okay, 1 times 100 is 100, 9 times 10 is 90, and 2 times 1 is 2. So we add all these together, 100 plus that position is 90 plus 2, that equals 192. Okay, we are so used to decimal values, we just look at them and we know what they represent. Now, similar thing goes on the binary. Depending on where the position of the digit is, then that digit will represent the number it occupies. So positional values, we start with 1 here, then 2, 4, and 8. So if we take a binary digit 1, 0, 1, 0, that means 1 here is occupied on this position. This digit represents 8. So 1 times 8 equals 8. Here we don't have anything, so we have a 0. Then 1 times on this position there's a digit representing 2's, so 1 times 2 equals 2, and then we don't have anything on the zeros. And we add 8 plus 2, that's 10. So 1010 in the binary equals 10 in decimal. So we take a few more examples. So in this example, we take another one, 0101 in the binary. So we put 0 on 8s, 1 on the 4s, 0 on the 2s, and 1 on the 1s. We ignore the zeros, so we just add the 1s. This digit here represents 4. So 1 times 4 is 4, and this digit represents 1s. So 4 plus 1 is 5. So 0101 equals 5 in decimal. Again, another one, let's take another binary digit 1111. So this digit here represents 8. The next one represents 4. Next one represents 2. And the next one represents 1. So 8 plus 4 plus 2 plus 1 equals 15. So binary numbers 1111 in decimal is 15. Now we can take a few more examples, but in this time we are using octets involving 8 bits. So for example, if we have 11000000, so this one here represents 128. So the numbers go 1, 2, 4, 8, 16, 32, 64, and 128. So we just place the ones and zeros on the table. So here, this number represents 128. This one here represents 64. And the rest are zeros. Zeros we just ignore. So 128 plus 64. That equals 192. So binary number 11000000 equals 192 in decimal. So if we take another number, a binary number 10101000, we place on the table, we ignore the zeros and we just add the ones. This one here represents 128. This digit here represents 32. And this digit here represents 8. So 128 plus 32 plus 8 will give you 168 in decimal. So IPv4 address structure. IPv4 addresses are 32 bits in binary numbers. So 32 of these zeros and ones. However, for ease of use by people, binary pattern representing IPv4 addresses are expressed in dotted decimal. This is the first accomplished by separating each byte, 8 bits, of the 32-bit pattern called an octet with a dot. It is called an octet because each decimal number represents 1 byte or 8 bits. So for example, in binary, this is IPv4 address. This is what the computers will see. But for us, so we can understand it better and we can represent this address better, is we separate it on 4 octets. So we divide it in 4 of 8 bits. 8 bits, second octet, third octet, and fourth octet of 8 bits. Then we convert these bits into decimal. So these 8 bits represent 192. These 8 bits represent 186. Sorry, that should be 168. And then these bits represent 10. These bits here represents another 10. Let me just change that. So this one here represents 168. Okay. Now, conversion from decimal to binary, it's the other way around. So now we have a decimal number of 168 and we want to convert this number into binary. What is ones and zeros? So again, our target is to convert 168 to binary. We start with the highest number in octet, which is 128. This one here. We compare to our target number of 168. So our target is 168 and we compare 128. If 128 is equal to or lower than our target number, which is 168, we place 1. We put 1 there in that position of value. And we remove 128 from our target number of 168 in this case. So yes, 128 is lower than 168, so we place 1 there. And we minus 128 from our target. So 168 minus 128 equals 40. So our new target is 40. So we placed 1 there. We move to the next positional value, which is 64. This one here. If 64 is equal to or lower than our target number, 40 in this case, we place 1 in this positional value. But 64 is not equal to or lower. 64 is higher number than our target, so we leave that field as 0. We don't place anything there. We move to the next positional value, which is 32. If 32 is equal to or lower than our target number, 40 again, we place 1 in that positional value. It's true, 32 is lower than our target number, so we place 1. And then we remove 32 from our target, 40. So 40 minus 32 will leave us 8. So now a new target is 8 we left. So we move to the next positional value. You get the point how it's going there. 16. If 16 is higher, lower or equal to, we put 1. But it's not. 16 is higher than 8, so we leave that as 0. We move to the next position value, which is 8. If 8 is equal to or lower than our target number, 8 in this instance, we place 1 in that position value. So 8 is equal to our target, so we place 1 there. And we remove 8 from our target number, which is 8. So 8 minus 8 is 0. If we get 0, then all bits afterwards are equal to 0. So we put 1, and then the rest are 0, 0, 0. So 168 decimal equals to 10101000 in binary. Okay. Now I have some for you to practice, so here you can pause the video and try it yourself. I have numbers 240 for you to convert them to binary, and 123 decimal number to convert to binary, and converting 255 to binary. Okay, so pause the video, see if you can convert these. The next slide will be showing you the answer. Okay, coming back now. Next slide is going to show the answers, which is, okay, here we go. 240 converted to binary is 11, 11, and then 4 zeros. So 128 plus 64 is 192, plus 32 is 224, plus 16 is 240. The rest are zeros. Converting 123 to binary, so 128 is higher than 123, so we place 0 there. 64 is lower than 123, so we put 1 there. And then the rest you can continue counting. So 123 minus 64, whatever it leaves you, and so on. But 123 in binary is 0, 1, 1, 1, 1, 0, 1, 1. 64 and 32 is 96, and 16 is 102. 112, and 8 120, plus 2 122, plus 1 123. Converting 255 to binary, you have all ones. When you add all the bits, 128 plus 64, 192, plus 32, 224, plus 16, 240, plus 8, 248, plus 4, 252, plus 2, 254, plus 1, 255. So 255 decimal is all ones in binary. Network portion and host portion of an IPv4 address. IP address is made out of two parts. You have a network portion and a host portion. To define the network host portion of the address and the device, to define the network and host portion of the address, the devices use a separate 32-bit pattern called a subnet mask. So subnet mask is going to tell us which portion is a network and which portion is a host. The subnet mask says where to look for these portions in a given IPv4 address. For the host, for the network, the subnet mask will put ones. For the host, the subnet mask will be zeros. So for example, all ones here, they do represent a network address, and zeros here represents a host address. The bits within the network portion of the address must be identical for all devices that reside in the same network. So anything that is 192.168.10, all the devices with this address, they will be classed as an insane network. The bits within the host portion of the address must be unique to identify a specific host within a network. So for example, this 10 here is a host address. So network portion and host portion of IPv4 address, again we have a subnet mask, and the subnet mask is going to tell us which is a network portion and which one is a host portion. Where is a network, we'll place ones, where is host, we'll place zeros. So the different subnet masks that we could have is all 255, all ones. We could have 7 ones and 1 0, which is 254. So if you add 128, 64, 32, 16, 8, 4, 2, it's 254. We could have 252, 248, 240, 224, 192, 128, and 0. These are the possibilities for your subnet mask. There's a subnet mask rule that says ones, they have to be contiguous together on the left, and the zeros, they have to be together on the right. So you can't have mix and match. You can't have a zero somewhere in the middle here. The ones on the left, zeros on the right. That's a network, that's a host. Now, when you convert these, all ones is 255. These ones again, 255. These ones again, 255. And then all the zeros equals to 0. Network prefixes. The prefix length is another way to express the subnet mask. The prefix length is the number of bits set to 1 in the subnet mask. It is written in a slash notation, / followed by the number of bits set to ones. For example, if the subnet mask is 255.255.255.0, there are 24 bits set to 1 in the binary version of the subnet mask. So the prefix length is 24 bits or /24. The prefix length, the prefix and the subnet mask are different ways to represent the same thing, the network portion of the address. Networks are not always assigned a prefix for example 4/24. Depending on the number of hosts on the network, the prefix assigned might be different. So for example here we have a prefix 24. That means there's 24 ones on the left here, and there's 8 zeros. So that subnet mask is 255.255.255.0. The prefix length could be 4/25. So there's 25 ones and there's 7 zeros left. So the subnet mask is 255.255.255. This bit here represents 128. So .128. Prefix length 26 means there's 26 ones here. Now the address in decimal will be 255.255.255.192, because this is 128, this bit represents 128, and this bit represents 64. So when you add those two together, it's 192. We could have prefix length 27, /27. That means again 27 ones, or decimal 255.255.255.224. The reason 224 is 128 plus 64 plus 32. So that's 224. So you can see what you have to do is add the numbers, the prefix length, and it will give you the subnet mask. So for example, this one, last one, is 4/30. There's 30 ones on the left, and there's 2 zeros on the right. So the subnet mask 255.255.255.252 means that this 8-bit here represents 255, another 255, another 255, and then when you add these together, it's 252. Okay, but we could have, it's not only 24, 25, 26, we could have 16, 17, 18, 19, anything, 8, 9, whatever. So here we just, for now, you should understand the class C. So examine the prefix length. For example, the network address 10.110/4/24 is like this. On decimal is 10.1.1. The last 8 bits we represent in on binary. So you can see it's all zeros. First valid address. Now this address you can't assign to hosts, because this address is representing the network address. First valid address is 10.1.1.1, which is 10.1.1. All zeros, and they start with 1 there. And then we have the range, different kind of addresses in the between, until we reach the last valid address. Last valid address is 10.1.1.254. So 10.1.1. all ones, and the last one is 0. So here we have a different range, different combinations of zeros and ones, until we reached all ones, and the last one is 0 here. So broadcast address is 10.1.1.255, which means 10.1.1 in the binary, all ones. So the zeros we can't give, because that represents our network. The ones we can't give to a host, we can't assign it to a host as an IP address, because that represents everybody. So we have to say -2 here, or minus the network address and minus the broadcast address. But we have 8 zeros for us to assign as a host to the host. So the calculation is 2 to the power 8 minus 2. So we have 254 different IP addresses we can assign to the host. So for example, 254 different combinations of zeros and ones that could be happening in here. Okay, 2 to the power 8. I'm going to open the notepad so we can see that. 2 to the power 8, what it means is 2 times 2 times 2, 8 times like this. 4, 5, 6, 7, 8, like this. So 2 times 2 is 4. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. Times 2 is 64. Times 2 is 128. Times 2 is 256. So this one equals to 256. We have to take away the network address and the broadcast address. So -2. That will give us 254 different kind of addresses. So if you have 8 zeros, those two here represent zeros. If you have 8 zeros, we will get 254 different addresses. If we have a network mask or network address 10.1.1.0/25, this is representing there's 25 ones we can't use, or we can't do anything with them, we can't change, but we have 7 zeros left, right? So the first valid address will be 10.1.1.1, and the last valid address will be 10.1.1.126, right? And that broadcast address will be 10.1.1.127. all ones there. This 0 here is not changed. So because we have 7 zeros left, right? So we can only calculate up to 7. So if we open the notepad again, this time same again, 2 times 2 times 2, 7 times this time. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, 64, 1 to 8. So this is 1 to 8 minus 2 for our network address and a broadcast address. So we will have 126 different addresses that we can assign to the host. So 126 different combinations that we can have here with zeros and ones. So for example, 1, 2, 3, 4, and so on. Okay, so let me just go through this again. For example, say that we have address 10.1.1. I don't know, 0/28, right? So what is that /28? 28 means there's 28 ones. So 1, 2, 3, 4, 5, 6, 7, 8. Let me copy that. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. That's 28 ones. That's what we say. /28. That leaves us with 4 zeros. 0, 0, 0, 0. So that's because IPv6 is 32 bits, yeah? So 28 up to here, 29, 30, 31, 32. If I convert this into decimal, it's 255, yeah, all ones. That's 255 again, all ones, and 255 again for all ones. Now, next one, we have to convert this. So 1 to 8, this bit represents, plus 64, that's 192, plus 32, that's 224, plus 16, that's 240. So 240. The IP address is, I'm representing the subnet mask 3 different ways. I can represent it in decimal like this, I can represent it in binary like this, or I can represent it with a prefix length /28. Either way, you are telling the same thing 3 different ways. So how many host addresses can we have at 4 zeros? Well, the formula will become 2 to the power of 4 minus 2, right? So if it's 2 to the power of 4, it's like saying 2 times 2 times 2 times 2, 4 times. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this will equal with 16. Minus 2, we'll have 14 different combinations that we can have, or we can assign 14 unique IP addresses. We'd say minus 2 because the network address and broadcast address, we can't assign it, right? So what is that 14, for example? Let me just take this different kind of. So if I have this, again, the same number, right? So that's my network address. I can't assign it. So you will be like dot the first one, right? I don't want to confuse you here now. Here, the first one will be like this. The second one will be different combination, will be 1, 0. The third one will be like this, 1, 1, and so on. So we can have 14 different combinations using these addresses until we reach all ones, like that. And that's our 255, that's our broadcast ID. Okay. Maybe I confused there a little bit because I use the subnet mask and the different kind of IP addresses. But you have to think, okay, how many zeros I have available? With those zeros, I can assign to the host, and then you can calculate how many hosts you can give per subnet. So IPv4 network, host, and broadcast address. There are 3 types of addresses within the address range of each IPv4 network. So each version 4 network has 3 different types of addresses. First address is network address. Like we said, a network address is a standard way to refer to a network. We can't assign that address to any PCs. The network address is like just imagine, okay, imagine like you are living in a house. I don't know. There's a five students. The house name is not very good to assign it, or you can't assign it to a student, right? That's represents your house. Now each student will have his own unique IP address, right? And then the broadcast address is if you want to talk to everybody within that house. So the network address represents your, for example, like your house, or the network address. Host address represents every end device requires a unique address to communicate on the network. In IPv4 address, the value between the network address and the broadcast address can be assigned to end devices. So anything between the network address and broadcast address, you can assign it to addresses, to unique end devices. Broadcast address, the IPv4 broadcast address is a special address for each network that allows communication to all of the hosts on that network. So you have first address that represents the network, and the last address represents that, okay, if you want to talk to everybody in that network, use this address. And then the range between the network address and broadcast address, you can assign it to the end devices. First host and last host address. To ensure that all hosts within a network are assigned a unique IP address within that network range, it is important to identify the first host address and the last host address. Hosts within the network can be assigned to IP address within that range. So for example, the network address 10.110/24, the first valid address is 10.1.1.1. So if you look, these numbers are in binary. Then we have a different combinations that we can use here until we reach the last valid address, which is 10.1.1 and 7 ones and then 0 in the end. That's 254. The broadcast address is 10.1.1 and all ones, which is 255. Which means this is our network. We represent ourselves with 10.1.1.0. If you want to talk to everybody in this network, use this address 10.1.1.255, and then these are the valid different combinations that we can give to addresses to the host. We need to identify which one is the first valid and which one is the last valid address. Now, bitwise and operation. Now, when an IPv4 address is assigned to a device, that device uses a subnet mask to determine what network address the device belongs to. So to find out what network am I on, the device is going to use a subnet mask. The network address is the address that represents all the devices on the same network. When sending network data, the devices use the information to determine whether it can send packets locally or if must send to the packets to the default gateway for remote delivery. So for example, the host device is going to use a subnet mask to find out what network does it belong. It's going to use bitwise and operation, which when 1 and 1 equals 1. Anything else equals 0. So 1 and 1, 1. 1 and 1 equals again 1. 0 and 1 equals 0. 0 and 1 again 0. And 1 and 0 equals 0. Everything else, 0, 0 equals 0. So let me just write these down on the notepad. Here. 1 plus 1 equals 1. 1 plus 0 equals 0. 0 plus 1 equals 0. And 0 plus 0 equals 0. Okay, this is bitwise operation, yeah? So where 1 and 1 equals 1, everything else equals 0. So when we calculate to find out what network we belong to, 1 and 1 equals 1. Again, 1 here. Then everything else here, we have 0 and 1 equals 0. Again, 1 and 1 here equals 1. 0 and 1, 0. And then we continue until we reach here. 1 plus 0 equals 0. 1 plus 0 equals 0. So now this device has found out, okay, my network address is 11000000101010100000001010 and all zeros. Or if we convert it in decimal, we have 192.168.10.0. So now it knows, okay, well, my IP address, if I open the notepad, my IP address was 192.168.10.10. My subnet mask is 255.255.0. So when I did the bitwise conversion with this, I found out that my network address is 192.168.10.0. So now the end device knows, okay, well, this is my network, yeah? So 192.168.10.0. So if I need to send anything, for example, destination IP address is 192.168.10.5. 10.5. Now this has already done the conversion. It knows, okay, well, this is in my network. 192.168.10.5 is in my network, so I'm going to send it locally. I don't hate to bother my gateway. But if destination, for example, is 192.168.20.5, now it knows, okay, well, .20 is not in my network, so I'm going to send it to my default gateway. On this demonstration, I will show you how to assign a static IPv4 address to a host. I did this on chapter 6 as well, so you should, if you want to see it more, you can actually visit chapter 6 as well. Okay, but I have this PCA, so I'm going to assign IPv4 address. So click start, and then we go to the control panel. You will not get this. Hopefully your PC will be licensed. This PC is used for training, so it's not licensed. So network and internet, network and sharing center, and we use local area connection. We can get through there. We can press that link there, or we can go change adapter settings. Okay, if you do change adapter settings, it will show you all the adapters you have. Here you can right click and say properties, and it will open the properties for that adapter. Then we have to select TCP IPv4 and go to properties. For some other some other training, it's already got IPv4 static IP address, but usually it would be like this, something like this. Okay, let me change that and press OK. Click on there, IPv4, Internet Protocol version 4, properties. It will be like this. And then if you want to give a static IP address, you say use the following IP address and give an IP address. For example, 10.1.1.1, 255.255.255.0, and then default gateway. Okay, so say that I pick one IP address here. For example, I'm just going to pick 172.16.28.0, right? And that's my subnet mask. What do you think is going to be my sorry, not 0 here, so say 101, the subnet, the network ID. The network ID will be 172.60.28, because that's what subnet mask is telling me. And then we have to put the gateway, the default gateway, in case that we want to go out of our network. So 172.16.28, for example, .1. Okay, I'm picking these from my mind, so they are not even there. They don't exist. Okay, next thing I want to show you here is this alternate configuration. Alternate configuration is, okay, I set this to get an IP address from DHCP server. If there is no DHCP server in the network for some reason, can't contact, it will assign alternate address. Now, alternate address by default, if you don't do anything, they are set to 169.254.something.something. That something is anything from 1 to 255. Or it could be 0 as well. It could be 0. Right. Now, it will set that to that. So, for example, 169.254.100.200, something like that. It will pick random number. First, before it actually assigns it, it's going to ping that IP address, just in case if somebody else doesn't have it. But the reason is, so it still will be able to communicate locally with network devices in case the DHCP server is not available. You can set to different, that's the default, but you can select an alternate configuration here. You can use automatic private IP addressing. That's our what we did here in the notepad. 169.254. That's something. Let me just get rid of these, because it's something. Or you can use it yourself. You can set, okay, well, if you can't contact the DHCP, I want you to give these IP addresses to my device. Okay, moving on. IPv4, Unicast, Broadcast, and Multicast. An IPv4 network, the host can communicate one of 3 ways. It can communicate through Unicast, the process of sending a packet from one host to an individual host, so from 1 to 1. IPv4 host addresses are Unicast addresses and are in the address range of all the zeros to 223.255.255.255. So a unicast address, a unicast communication is like me, I don't know, speaking to my friend Tom. It's like, first I get his attention, I say Tom, and then he says, oh, hello Astrid, and then that communication between me and Tom is one-to-one. Broadcast address, the process of sending a packet from one host to all hosts in the network. The broadcast is like, okay, when I'm lecturing in the classroom, everybody's listening and I'm speaking. My message is being broadcasted to all my students. Multicast is the process of sending a packet from one host to a selected group of hosts, possibly in a different network. The globally scoped addresses are 224.0.1.0 to 238.255.255.255. Now, multicast, when you think, okay, if I'm doing it in the classroom, if I have a classroom, say I have 10 students, and 5 students, I group them in group A, and another 5 students, I group them in group B. The multicast is when I say, okay, group A, let's do this. I'm doing a multicast message. I'm not speaking to all my students, I'm speaking to a group of students. Okay, same happens here in relatively in the PC on the networks. An IPv4 multicast address 224.0.0.0 up to 224.0.0.255 are reserved linked local addresses. A router connected to the local network recognizes that these packets are addressed to a linked local multicast group and never forwards them further. So they will not send these addresses, these multicast addresses will not go from one network to another network. They are in the link, only on the link. Some of the addresses will be like, I don't know, 224.0.0.9.10, .5, These are some of the dynamic routing protocol addresses that they use. So the globally scope, where you can send from one network to another network on the internet, for example, the range is 224.0.1.0 up to 238.255.255.255. Public and private IPv4 addresses. Private address blocks are hosts that do not require access to the internet can use the private addresses. So now, for example, imagine my home. Yeah? I have about 10 devices that use 10 IP addresses. Those IP addresses are unique, but are unique in my local network. They don't go to the internet, those addresses. When the device needs to go to the internet, they will be translated to public IP address. So at home, I have a private IP addresses. Now, this is the private IP address range that you could use. Now, these are free to use. You can go home, you can go to your work, to your business, and just choose any of these ranges and start using them. The range is from 10.0.0.0 up to 10.255.255.255. That's the private range. The second private range, which is class B, is 172.16.0.0 up to 172.31.255.255. And the third range is 192.168.0.0 up to 192.168.255.255. Now, this is the private range. You can use them as you wish. But the thing with this is that they cannot go to the internet. So your router is not allowed to send them to the internet. They can try, but any internet router it will block those addresses. Private addresses are defined in RFC 1980. When you think of RFC, it's request for comments. So the open paper, white paper that you can go and have a look. What are the definition of private addresses? Just over Google and search RFC 1918. You will see a big white paper explaining the private addresses. Hosts in different networks might use the same private space addresses. Packets using these addresses as the source or destination should not appear on the public internet. For example, imagine I'm using private address 192.168.1.1 at my home. You could be using the same IP address at your home, 192.168.1.1. It doesn't matter. It's still unique because my private address will never go to the internet and it will never reach your home, and your private address will never reach my home. So as far as they are always separate from each other, so they will be okay to be used. We have another RFC 6598 IANA reserved another group of addresses known as shared address spaces. These shared address spaces are similar to RFC 1918 private addresses, but they are used by ISPs. Now, they are not globally routable. These addresses are intended only for use in the service provider network. The shared address block is 100.64.0.0/10. We have some addresses, they have a special use, IPv4 addresses. They are network and broadcast addresses. Do you remember? We don't assign network address or broadcast address to the host because we need a network to represent our network address. We need a broadcast address if we want to speak to everybody in that network. So they are the special addresses that we cannot use. Then we have another type of addresses, loopback addresses. Loopback addresses are intended for testing. You can ping yourself to make sure you installed your network card correctly and your TCP/IP is working correctly. So they can't assign to the host. The addresses are 127.0.0.0 up to, that's the range, up to 127.255.255.255. All of them are reserved. Then we have a link local addresses. Link local addresses, remember I said APIPA. If you can't contact DHCP, you're going to assign yourself an IPv4 address. An IPv4 address are in this range 169.254.0.0 up to 169.254.255.255. Then we have another special use IPv4 addresses that is called testnet addresses, and these are set aside for teaching, learning, like what we're doing now, using in documentation, and network examples. These are 192.0.2.0 up to 192.0.2.255. And then the last one is experimental addresses, which are from the range 240.0.0.0 up to all 255, 255, 255, 254 are listed as reserved. So we can't use them. These are for future research experimental addresses. All time we used to have class full addresses, right? So all addresses, they will on the class full range. So you have class A, you have class B, class C, class D, and class E. Now, class A was designed for big businesses, right? So we have, for example, Apple went and purchased an IP address. It wasn't like, okay, how many addresses you want? It was more like, what class do you want? Do you want A, B, or C? Now, A, as you can see here, A will give you 16 million hosts per network. 16.77214 hosts per network, right? That's quite a lot of public IP addresses, and not a company will need so many IP addresses. Now, then that was designed for big major companies. Then we have the class B for medium-sized companies, and they were thought class C was for small businesses. It didn't work very good because there was lots of unused IP addresses being sold to companies, and they were staying unused. So then we moved on to something called classless addresses, and formal name is classless interdomain routing, CIDR. Created a new set of standards that allowed service providers to allocate IPv4 addresses on any address bit boundary, prefix length, instead of only by class A, B, or C addresses. So they saw the class full addresses. It wasn't working very good because class A, I mean, not many companies are going to need 60 million addresses. Maybe Apple will need it, but I don't know. There's not so many companies as big as Apple who will need so many IP addresses. So they created classless, where the ISPs, they forgot this A, B, and C. They were just saying, okay, well, how many addresses do you need? I need 10. Okay, fine, you can have 10, and so on. Now, the range for classes is class A, for example. The range is the first octet we're talking about, 1 to 127, right? So 1 to 127, or in binary octet all zeros up to 0 1 1 1 1. Okay, so let me open the notepad again here. Class A, for example, we have 1, that's the first octet, .0 second octet, third octet, fourth octet. The range is up to 127.255.255.255. That's it. 3 to 5 hours. Now, in the first octet, it starts with 0. Now, this 0 is important because it does not change. On class A, it always will stay 0. Now, we have another 7 zeros. 1, 2, 3, 4, 5, 6, 7. And the range is up to, so we said the first 0 never changes. And then all ones, 1, 2, 3, 4, 5, 6, 7. So we use different combinations here from 0 up to when we got all ones, and that's 1.000 up to 127.255.255.255. Class B range is 1 to 8, the first octet, .0.0.0 up to 191. Sorry, I was thinking about something else. 191.255.255.255. Now in class B, you have to think, okay, it starts with 10. The important those two bits that will never change. It always will stay 10. 1, 2, 3, 4, 5, 6 left. And we said that it's always going to be 10, and until we reach all ones. So 1, 2, 3, 4, 5, 6. Okay. So as you can see here, nicely colored. That's the reason why they're colored, because they will never change. So class B is always will start with 10. Class C starts with from 192 up to 223.255.255. So if I open the notepad again, so 192.0.0.0 all the way up to 223.255.255.255. That's class C address. The network, so we have a network and the host parts of the address. So in class A, we had the first octet was a network, and the last 3 octets were the host, like, or represent 255.0.0.0. With this, we could have 128 networks, and each network can have just above 16.7 million addresses. Class B address, the first 2 octets will represent a network. Sorry, and this with these 2 addresses, 2 octets, we could have 16,384 networks, and each network will get 65,000, just above 65,000 hosts. Class C, we will have 2 million different networks available, and each network will have 254 hosts. Class D is reserved for multicasting, and then the last one, Class E, is reserved for experimental. Assignment of IP addresses. Internet Assigned Numbers Authority, IANA, manages the allocation of IPv4 and IPv6 addresses. Until the mid-1990s, all IPv4 address space was managed directly by IANA. And then at that time, after the 1990s, IPv4 address space was allocated to various other registries to manage for particular purpose or the regional areas. These registry companies are called Regional Internet Registries, RIRs. There's a 5 RIRs. First of all is African Network Information Center. The next one, that's deal with African side managing the IPv4 addresses, N6. Then we have Asian Pacific Network Information Center. Then we have an American registry for internet numbering. Regional Latin American and Caribbean IP address registry, and Resource EIP Europeans for Europe. The thing is with IPv4, because IANA was assigned in IPv4 addresses until 1990s. Again, there was not a proper structure, right? So, for example, think of addresses assigned. Okay, first address goes to North America, second address to Europe, third address goes to Africa, fourth Australia, and so on. Now, the problem with that is that computers on the internet, they're going to have a massive routing table, right? They're going to keep all the addresses. Now, they thought, okay, well, this is not very good. It's not working very good. So let's create these regional internet registries, and we give them a block, saying a block from 100 up to 200, it's in Europe. From 201 to 300, or whatever, the blocks there you have. There's not 300 on IPv4. But the blocks, say, 1 to 10, North America, 11 to 20 South America, 21 to 30 Europe, and so on. This is a structured way of giving IP addresses. You're giving a block to registries. Last thing is the ISP tiers. ISPs are designed by hierarchy based on the level of connectivity to the internet backbone. Each lower tier obtain connectivity to the backbone via the connecting to the higher tier ISP. So if you think of it, okay, this is the backbone, this is the internet backbone. So we have tier 1 ISPs that are large national or international ISPs that are directly connected to the backbone or internet backbone. Then we have a tier 2 ISPs, generally focused on business on customers, so tier 2, and then we have a tier 3. Often bundle internet connectivity as a part of the network and computer services contract for their customers. So these are the companies that we deal as a customers, and then they deal with their own ISPs, and those ISPs are deal with national ISPs, and then to the internet backbone. Okay, now we move on to well, that's it for 8.1, and I'll see you in section 8.2, IPv6 network addresses.